So I'm going to start streaming, see if we get any more folks, and if not, thank you for coming today. Because you know what? Ask and you shall receive. Wait for it. You're like, what did I ask for? So, Shinji, did I say your name correctly?
Yes.
Okay, just for you, I have a new, let me see here. My copy isn't, but this, I posted this earlier today. I have an example 5B with a negative binomial model, just for you.
That's awesome. Thank you.
You're welcome. I don't know why it's not updating itself, but it should be right here. So I finished it earlier today. And for those of you who are asking me when I'm going to teach longitudinal again, I'm going to do it in this class. I just decided, because I don't know when it's coming back. And I have several 3-level data examples that have the bottom level as longitudinal, and I thought, well, I'm going to reuse those. So we're going to have a crash course on all the ways that what you've learned maps onto longitudinal, and then we're going to put it together in 3-level models of longitudinal clustered data. How's that sound? Yay! Okay. So the other thing is that as I developed the examples using generalized models and cross models, and I know this is true for 3-level models, the answers from SAS and Stata will continue to diverge in ways that makes it impossible to use the homework system. So I'm trying to decide what would be a useful approach for homework for the last two. So I'm interested if you have any thoughts on that to send them to me either now or via email. I'm not going to be able to do the same sort of thing, but what I can do is give you output and ask you to interpret it, or I could ask you to do a results section where I grade it by hand because I'd have to be able to check the numbers for each of you, that kind of thing. So I'm pondering what else I can do. I thought about that, and I'm not sure that I can. So here's the reason how this works currently. I generate individual data sets using each of your ID numbers as the random seed in SAS. And then I have a giant loop that runs all of your models on all of your data and spits out all of the answers into a database. I would have to be able to program Stata to do that as well, and I am not a Stata programmer. That's a skill set that I am unable to acquire in a short enough amount of time to make that work. So the other alternative, I think, would be to have not individual data sets. Then if it was like one set of answers, I could probably program it that way. But then that takes all the fun out of it, right? So I don't know. So I'm pondering this. Your next homework isn't due until the 18th, so I have a little bit of time to figure this out. So if you have any thoughts on what aspects of the homework would still be good to keep or other things you think would be useful for your learning, let me know. As I said, I'm eager. So yes, we'll do some longitudinal. We're doing some negative binomial on Thursday if we get through this stuff. And today we have generalized after we go over our quiz. Formative assessment. I'm in the College of Education, right? So we have to use the educational buzzwords like formative assessment. I'm doing student-centered teaching, I think, trying to meet where you are, bring you to the truth, right? Capital T truth. So I have a real-world story problem for you. Pretend that you're a reviewer of this manuscript or that you're doing statistical consulting and someone comes to you for help and says, did I do the right thing? So this is the question here. So I looked at your answers and I realized there was a point of confusion as to what one of the variables meant. So let me just go over what I had in mind. If you want to put another answer in the system, you can do another attempt. I set it to take multiple attempts, and so if you want to, for your own writing, but you get credit just for participating, as I've said before. Yes, they're both in there. So a researcher wants to determine the effect of an intervention assigned to teachers on a student-level outcome. So we have students nested in teachers. So there's 500 total students and 20 teachers. So students are level 1, teachers are level 2. She wants to ensure that the intervention denoted as group. I had intended for group to be a level 2 predictor, a teacher level thing, where some teachers are control teachers and some teachers are intervention teachers, because that's almost always how it is because of contamination. It's hard to do an intervention at the student level without getting the students mixed up. So I apologize for not making that clear, but that's what I had intended, is this is a level 2 predictor. And she wants to know if it is equally effective for students of different abilities. And she has a student level covariate called ability that already has a mean of 0, so that makes it easy to fit the model uncentered. And this is what she fits. So proc mixed code for the setup, stata code down here, a main effective ability, a main effective group, ability by group, these are all the fixed effects, a random intercept across teachers, and that's it. So I asked you to identify 3 areas of concern with respect to estimation, fixed effects, and random effects. So first off, we'll do first off. Who wants to share what they think is wrong with this model? In any order. You can tackle estimation, fixed effects, or random effects. What's the most glaring thing? That's the most glaring thing to you? I'll take that. That is correct. So let's change that to Rimmel.
Because what she did is biased, right? Okay, because my rationale was that Rimmel is unbiased since it doesn't assume fixed effects are known. And she also didn't ask for the ICC.
ICC is typically not of interest unless it's an empty model. I mean, that might be something, but it's hard to imagine that a conditional one would be. So yeah, is this sample size here, 500 students within 20 teachers, is that a small sample or a big sample? It is small. 20 is what makes it small. So the level 2 random effect variances are going to be underestimated by ML. For the reasons Kayla just said, because it assumes the fixed effects are known. So the random effect variances and covariances will be too small under ML, which translates into standard errors that are too small and type 1 error rates that are too high. So we should be in Rimmel, if at all possible. That is actually the default in Stata. And I was sort of tricking you here because if you don't have ML in Stata, it won't let you do Satterthwaite degrees of freedom. Degrees of freedom are only an option if you're using Rimmel in Stata for reasons that I don't know, but that's what they have. So this should be Rimmel. So that's one problem. That's an easy one to fix. Let's tackle the fixed effects of her model, where ability is a level 1 predictor, group is a level 2 predictor, and she also fit a cross-level interaction. Cool or not cool?
Not cool.
Not cool. Dear Reviewer 3, not cool. Dear author, not cool. All right, why is this not cool? Smushed. What is smushed specifically? You can read your answer because it was a good one.
Oh, it was?
Yeah.
Oh, okay. The model doesn't account for the effect of being in a group with a higher average ability prior to the introduction of the treatment.
Yes.
Compared to a group with a lower average ability.
So smushed is correct, and the way that you phrased it is also correct. When you put in a level 1 effect, an effect of a level 1 predictor at level 1 only, you are saying there is no contextual effect. Or in this context, that the average ability of the group you're in, the teacher you're with, doesn't differentially affect your score. So there are 2 ways to fix this model in which it is unsmushed. What would be the way that is least likely to be screwed up, in my opinion?
Group centering.
Within group centering, right? So we would want to make noob variables like within teacher ability equals like teacher mean ability, can't spell, it-t, and it would be ability minus teacher mean ability. And then we would have teacher mean ability as the other predictor. So I would replace that one variable with within teacher ability and teacher mean ability. Do I need to do anything else with respect to ability? Yeah. Which one of those goes here? She's concerned that the effect of the intervention would be different for students of different abilities. Which of those two predictors maps onto that idea? That the effective group varies by student ability.
It's a student's ability. It should be within.
I would think so. However, so that lets the effect of group vary as a function of how able you are relative to your peers. Although she didn't think of it that way, it's also possible that how able your peers are matters too. The effective group is different in different classrooms. So I would argue both. Now, if group is a level 2 variable, do I have to worry about smushing for it? Or is it fine? Should be fine, yep. Because I don't have 3 levels. That's why it's fine. Stay tuned, ...
Can you put it in words? So, because I have battled this in my head, so I ended up just doing it just in case, even though that's wrong. Can you explain why at level 2, like how would you interpret it versus the way you explained with like how your within ability for each teacher can affect the student at different levels?
So ability, even though you're thinking of it, or she's thinking of it as one thing, is 2 things. It's some teachers have smarter classes than others, and some students are more able within a class. So we are respecifying the model to allow each of those constructs to have a different effect. The ableness of your class relative to other classes, which is level 2, the ableness of you relative to the people in your class, which is level 1. So a logical prerequisite for having effects of ability at both levels is having variance in ability at both levels. So this would not make any sense if somehow all of the classrooms were equally able. If there were no classroom differences in ability, then there would be no way that team ability or teacher mean ability could do anything. But given that students are not often randomly assigned to classes, odds are good there's at least some classroom level variance in ability.
I think I was conceptualizing group wrong, because I was thinking, well, if group is control and the other one's intervention, what if there's differences within classrooms for like, who are not the same teachers?
The way that I was thinking of this more simply, just that each class is in group 0 or group 1. So, but let's tackle that as a special case. So group, in this case, is purely level 2. It only varies at level 2, so it can only have a level 2 effect. If it doesn't have variance at level 1, it can't have a level 1 slope. Now, it could, though, if some kids are control kids and some kids are treatment kids. Then the proportion of kids that are in treatment is a classroom level predictor. And then you'd have to worry about smushing the effective group too.
Thank you.
Okay. Does that help? Do you have questions on that? So now we can see whether or not the effective treatment depends on relative ability or whether the effective treatment depends on sort of mean ability of your class. So that's the fixed effects. Now random effects. Random intercept. So by putting an intercept in the model as a random effect, what has this researcher done? What is she saying about the dependency of outcomes for students from the same teacher? Is she handling the dependency? Yes, no, or sort of. We'll make this multiple choice. So question is, she has a random intercept in the model. So in putting in a random intercept, what is she saying about the dependency of outcomes of students from the same teacher? Is she handling that dependency? Yes, no, or sort of? She's handling some of it. So what kind of dependency does a random intercept imply? What kind of correlation across students from the same class? Constant or variable?
Okay, I put that, I thought she was supposed to put ability there because she wants to make the intervention the same at any level of ability.
So
Doesn't she want to control for that randomness that your ability has if she wants it to be the same? I mean, maybe I'm totally wrong.
So do you want it instead of intercept or in addition to? In addition to, yeah. And which ability? We got two of them now.
Within, for sure.
Within for sure. Because within is level 1, right? The effect of level 1 ability can vary over level 2 teachers. How about the other one? Teacher mean ability, the level 2 predictor. Does that go here or no?
I didn't include it.
You did not?
No, but maybe I was supposed to.
Can you have a level 2 predictor have a random effect over level 2 units? Nope. Doesn't go there. So this extra slope is a logical prerequisite to testing this cross-level interaction. Why is it that in some classes, student ability matters more? Well, maybe it matters more in the treatment rooms than in the control rooms. But the idea that in some classes ability matters more, that's a variance to be explained. How it gets explained is by the cross-level interactions with that random slope.
I didn't really think about this before you asked, because I just assumed that we should keep intercept there. Why would we not, and what does it, how do I interpret that in words, what it's doing? Because I know how to interpret like ability in words. What is intercept doing?
Let me show you a picture. Picture is worth 1,000 words here. Let me get you a picture. This. Intercept is the shift in y between groups. So if you put in a random slope with no intercept, that's the same thing as saying all these slopes are like on top of each other but at different angles. So no intercept would be that every group has the same mean on y, which is pretty unrealistic.
So you would always put that in different.
I would say yes. Some people might argue with me, but I would say yes.
Why would they?
Because the presence of random slopes predicts there is some point on the x-axis at which the variance across these lines would be 0 or very close to it. And if that is the centering point of your model, there may be no intercept variance at that point, and thus it looks like the intercept doesn't help. I would argue that you need it because if you centered somewhere else, it will show back up. And so I would allow it to be there because it changes as a function of centering. So to me, the intercept is always here in some way, shape, or form. So yes, what happens if this cross-level interaction is tested without this random slope? If the random slope should be there, if it's significant and you don't put it in, those cross-level interactions will have way high type 1 error rates. Like 40–50%, like way high. Because their standard error has to have that random slope variance as part of it. Otherwise, it's too small and the p-values are too lenient. So before putting in any cross-level interactions, we want to test whether the level 1 part of the cross-level interaction needs a random slope. How are we doing?
So to answer the research question like she proposed, do we look at the beta weights for both the two interactions simultaneously, or?
Yeah, I would argue that she didn't phrase her question specifically enough because student ability is both of these things. So I think you look at both of them. I think you interpret them both for what they are.
Like separately?
Mm-hmm. They, what's the word I want? They're complementary. And I don't mean like free, like here's some complementary snacks, like they work together complementary.
So is it possible to not include within ability in random statement and also not include within by group interaction?
So you want to take this out
And also
and take that out?
Yeah. So what kind of assumptions do we make if I fit the model?
There's nothing wrong. If you take those things out, you're saying there's 0. So there's no smushing problem. You're allowing the effective group to moderate level 2's effective ability, but not level 1's, which means you're saying it doesn't moderate level 1's. So the effect of being more able than another student is fixed. It's the same for all teachers, and it's the same for all groups. It's just this number right here. That's what you're saying. So whether or not it's okay to do this is a series of nested model comparisons. So how do I test if I need this right here? How do we test random things? Log likelihood differences, yep. How do we test fixed things? Wald test, yeah, stare at the p-value that shows up next to it. You can use those p-values because each of these fixed effects has a null hypothesis of 0 that's a reasonable thing. They're not on the boundary. Okay. Now, do you want to talk about the other way of setting this up for grand mean centering? Yeah? So what if the researcher's like, well, but I read this article and they said that my theory thinks that I should use grand mean centering instead. Okay, if you must. So this and this change interpretations. They're not between effects, they're contextual effects. So the main effect of teacher mean ability is the extra effect per mean, unit mean change in going to a classroom that has lots of smart kids after controlling for how smart you are in the control group. And then this is how that contextual effect differs in the intervention group. Now let me put this model. Now can I do that? Can I take out the level 2 contextual interaction and have it be okay? Yeah, see this uncertainty, this is why I said the other way is easier. Because anything that you take out, you assume to be 0, right? But here, if I take this out, it's not just that I'm assuming this to be 0. What I'm saying is that this term now is smushed. How group moderates ability is supposed to be the same for level 1 ability and level 2 ability. That's what this model means. So even though the main effect is unsmushed because we added teacher mean ability, this is a smushed interaction. Okay, so there. Yes, question?
Can you remind me what class means? Because in the homework we weren't supposed to use class, and I'm using it here, so I don't think I really know what it means.
Class is where you list variables that are supposed to be treated as categorical. I always put my nesting variables on there too because it makes it run faster. I think it has something to do with its sorting based on that, and I've seen instances in which I forgot it where it won't converge at all. So there's no analog in Stata to that. But this is where, like, if I had a grouping variable with more than 2 groups and I wanted it to make my dummy codes for me, I would throw that on there as well. And then in Stata, the analog to that is I dot.
Wait, is group supposed to be in a class?
Oh yeah, sorry, put it in the wrong one. Yep. Yeah, so the reason why I told you not to use it in your homework where if we had a binary variable is that if this is already coded 0, 1, what SAS does is make the highest group the reference. So it takes what used to be the 1 and it turns it into the 0 with respect to the model.
So if you've got something already done coded, don't use that.
Correct.
Okay.
It will reverse your coding and make you crazy.
So here, there are 20 groups.
We have 2 groups.
There are only 2 groups, but there are 20 teachers.
Yes, there's 10 in each. Mm-hmm.
So there are, okay. So for one intervention group, there are 10 teachers.
Yes.
And how many students
500 total.
per group?
Nope, just total. So,
You don't know
hmm?
how many students are in
Each class, 20 to 25-ish. You can pick. It's just a story.
Because there are sample sizes, different sample sizes. How can we control the weights?
So you can add weights if you want to try and get to some sort of level of representation. There's a weight statement in SAS, and then there's options for doing that in Stata as well. One thing to keep in mind is that when you have unbalanced sample sizes where the model is assuming that the within teacher variability is the same across all the teachers. So if you have really different sample sizes, that may not be the case, and you might have to build that into your model. You could also put in a covariate for the size of the class. If you think that smaller classes would do better or worse, for instance, you can put that in as a fixed effect. Okay. Other questions? Yes, sir.
I have 2 questions. First, so thinking about 20 teachers, as a quite small level 2.
Yes, it is.
Is there how many variables on level 2 we really can put?
19.
Okay, it's a nice one.
You could put 19 fixed effects in,
Okay.
which functionally what that means is that you can either have a random intercept across teachers, or you could have 19 teacher-specific dummy codes, in which case you don't have a 2-level model anymore.
Okay. Yeah. because the data like I'm dealing with right now is like it has only 16 universities at
Mhm.
level 2. Then like I want to see like some institutional characteristics like main effects like level 1 like a student like a learning experience and like the GPA's relationship. Then like I was just wondering like how many level 2 variables like I really can put. I already understand like it's 16 is quite small, but like
Yeah.
when I take
15.
like 3 institutional characteristics, like I feel like it's really too much.
Yeah, you have basically no power for between effects. So it may look like you don't need them, but to prevent smushing your level 1 effects, I would keep them even if they're not significant. Yeah, if you were to saturate your level 2 model, put in 15 dummy codes for your 16 countries, you wouldn't be able to test anything related to countries in terms of hypothesis for predictors. But yeah, you get 15. So.
And also like now we are doing like centering, right? So like
Mhm.
if we want to like standardize like those variables, like we have to standardize level 1 variable like within a group.
Yeah, so
Or
yeah.
design.
There is no such thing as standardized slopes in multi-level modeling. There's none. Because the basis for standardization is not clear for some of those. So like if you took one full variable and z-scored it, like you'd have to sort of re-z-score the halves, the level 1 part and the level 2 part. And then you would have to use group mean centering so that the y side is clearly delineated into the standard deviation of y at level 1 versus level 2. So in my textbook, I talk about, I do a pseudo standardization that's based on the same principle as pseudo R square, but there's not like an accepted way of doing standardized effects. There's standardized slopes because you have to standardize with the standard deviation of x and y, whether it should be full x or full y or just this part of x and this part of y, there's no real consensus on. So,
Thank you.
sure. All right. Others, yes. Let's see.
I'm sorry I came in a little bit late, so maybe you went over this already, but I'm still getting a little bit confused between effects and contextual effects.
Okay.
Can you help me understand, like, for this example, how you would interpret it, like how you would talk about it or interpret it?
Yeah. So this setup right here, this is contextual, and this is contextual. So these are the level 2 effects of ability after controlling for students' ability. So it's the extra benefit of going or being in a classroom with lots of smart kids after controlling for how smart you are. The between version that you get from group mean centering is not controlling for how smart the student is.
Like TM ability is between, right?
Mhm.
By itself.
Yep, and that's why this is the hard way to do it. So if you took out these two things, they're not contextual, they're between.
Yeah, I understand, because it has to have both, like, kind of like when we said, it's like in the homework, we have to explain if it increased or decreased, or that really confusing part that I always mess up on. that's always the contextual part, right?
Yep.
Okay.
It is confusing. There are lots and lots of people doing multi-level models in the world that screw it up. So if you find it confusing, you're in very good company. I've been trying to explain this for a good 10 years, and it still confuses me from time to time. But yes, we did this chart a while back. Might be worth revisiting. So this is what the terms mean and what variances should be affected. So if you're doing group mean centering, where you partition the variables into their variability at each level, then regardless of whether the level 2 part is in, the level 1 variable is within. Regardless of whether the level 1 variable is in, the level 2 is between. So under group mean centering, it is what it is. And if you don't put it in, you're saying it's 0. Just the same as in any type of regression model, right? If you don't put a predictor in, you're saying it doesn't matter. However, if you do grand mean centering or no centering at all, so if you pick a centering constant of 0, right, that's the same thing. all of the variability in the level 1 predictor is still there. So if you put it only in the level 1 model, it's smushed. Meaning what you're actually saying is that the effect at level 1 is the same as the effect at level 2. You're making two terms share one coefficient. If you put in the group's mean of the predictor in level 2 only, it's between. Once you pair it with the level 1 grand mean centered variable, it switches to contextual, and the smush switches to within. And that's because under grand mean centering, these two predictors are correlated. So their effects when put together are different than their effects when separate. It's their unique effects that you end up with when they're together, which compete against each other. And this switching back and forth of what it means makes me crazy. So that's why I like this way of doing it, because it is what it is. Okay, did that help? Okay. But yeah, the difference of between and contextual is whether or not you're controlling for the level of the level 1 variable. So in group mean centering, you've taken it out and there's only relative information. Whereas here, it's relative and absolute information at the same time. Okay. Other questions? All right, are we ready to move on then? To the next unit? Getting to do all of this with logits too? Woo! I was almost convinced. So let me ask some background. I think I asked this before, but this will help me figure out my pacing. How many of you have had generalized linear models before? Things like logistic regression, count regression, multinomial regression. Anybody? Okay, so you haven't had it, or you had it and it's like gone, so you may as well not raise your hand. That one? Gone, so not raising your hand? Pretty much? Okay, great. That makes it easy, because then I'm not like everyone's on the same page, right? How many of you have taken IRT, item response theory? Okay, so you have seen generalized linear models before, just with non-observed variables instead of real ones, but that's okay. So that's good then, that I have a lot of stuff here on just the generalized part. And I am going to probably not get to spend nearly as much time on this as I could. If you find this stuff really cool, then come back next semester, because I'm teaching a whole class on generalized linear models, but they'll be single level. So you guys are actually getting the advanced version right now, because we're taking everything that you've learned from multi-level and we're adding all of this to it. Yay!
Yay!
Yay! So we got some new terminology, some new friends to meet in terms of links and distributions. It's going to be awesome. All right, so ISed, generalized, what does that mean? Not normal. So the term general linear model, you know. General linear models are things like regression in ANOVA and ANCOVA. Those are models for residuals that are supposed to be normal. If you have some kind of outcome whose residuals cannot be normal, then you need a generalized linear model. And the same is true if you have multi-level data. So here we go. Clarifying distribution terminology. So there's a few new words that are going to start showing up that I want to make sure I define before we get into them. So the models that we've fit so far this semester, and in all of longitudinal last semester, for those of you who are with me, assume normality of the residuals at both levels. So the level 2 U's are supposed to have a multivariate normal distribution. The level 1 E's are supposed to have a multivariate normal distribution. That makes it easy, relatively speaking, to find the answers for the parameters that maximize the likelihood. So if we have a model that looks like this, for instance, with one level 1 predictor that's been group mean centered, for simplicity, I'm leaving the level 2 model out. You've seen this before. This is how the model builds a prediction for the variance. Another way of writing this same idea, where the fixed effects the design matrix for the predictors that have fixed effects, and gamma are in red. Z is the design matrix for the predictors that have random effects, and U is the random effects themselves in blue. Another way of writing it is like this, saying the conditional mean for each outcome is given by this thing. So it's kind of like y hat. Remember that from regression? This is like all the y's put together for one group. And so if we say, how is y supposed to be distributed? It looks like this. Y put back together again across levels is normal with a conditional mean from the model fixed effects and a variance of v. So v is level 1 and level 2 put back together again. That's marginal. So if I have this, z times g times z transpose plus r, that gets me v. So the idea is that the sum total of the variances and covariances across observations is a function of the level 2 random effects, variances and covariances, and the level 1 residual variances and covariances. Just shove them back together again, you get v. If I were to take the random effects part and instead add them to the conditional mean, like this, then what's left is r. And so then we're talking about the conditional distribution of y after controlling for the random effects is supposed to be with the level 1 residual. Am I out of time already? Damn, these classes go faster and faster each time. So yeah, the word conditional is going to mean after factoring out the random effects. What is the distribution like? And what these models up to this point have said is normal. Now we're switching out what conditional distribution we're using for the level 1 part after controlling for level 2. And level 2, the random effects are going to be shoved into the mean part, what's known as the linear predictor. So marginal is all of the variance across random effects and residuals. Conditional is referring to just the level 1 part. So I've talked about level 1 residuals as things that we could find, and that's fine and dandy when you have a normal distribution underlying your model. However, I can't really say that anymore because, as we'll quickly find out, there may not be level 1 residual variance as an estimated parameter anymore. Certain distributions don't have a separately estimated variance. So it's not that level 1 is perfect, it's that it's known as a function of the mean. So in normal land, general linear mixed models or general multi-level models, we have a level 1 that's normal, a level 2 that's normal, and so I can say the conditional distribution is multivariate normal. This is not the case going forward where we're out of normal land. So we have normal at level 2, but something else at level 1. So when we talk about the level 1 part, it's conditional. So terminology, words that go to Google by. Here's how they all stack up. So general linear models. General means normally distributed residuals. Linear means that the predictors enter linearly. So slope times variable plus slope times variable. That's what linear model means as opposed to like exponents and shit like that. The absence of random effects, having only fixed effects, means that only one dimension of sampling is assumed for the outcome. So everything you learned in intro stat, intermediate stat, correlation and regression, all that stuff that has to do with sums of squares and all that crap, that's under this umbrella right here. With the exception of logistic regression if you got to that in correlation and regression, but it doesn't sound like it's stuck. So we're starting over with that anyway. If you have one dimension of sampling still, but your outcome does not have a normal residual distribution, a normal conditional distribution, that's generalized linear models. I'm teaching that next semester as the follow-up to the intro class. Then where we've been this semester is general linear mixed models, where that term mixed is synonymous with multi-level, and it means that we have random effects and fixed effects. So each dimension of sampling can pick up a random effect, another kind of variability to go with it. And then if we put it together, generalized linear mixed models is fixed and random effects and non-normal conditional distributions. All together. It's going to be awesome.
So the non-normal part
Mhm.
refers to only level 1.
That is right. The non-normal is only level 1.
So So for the level 2 is still normal?
Yes.
Is that possible?
That is pretty much what you are stuck with in every software package. Theoretically, it is possible to change it. There's been some work suggesting it doesn't matter because level 2 are latent variables anyway, and so it's hard to pin down what their distribution is. But it's the exact same assumption that you make in IRT, for instance. Theta is normal, right? Factor scores are normal. U's are normal. So yeah, we're talking about the conditional distribution, the level 1 part specifically. After factoring out the random effects, what's left? We're trying to find different distributions for that. So there are all kinds of models that pair what's known as a link function, meaning some kind of transformation, we'll get to that in a second, with a different type of conditional distribution. So you may have heard of these. So for binary outcomes, unordered categorical outcomes, which is nominal, ordered outcomes, which is known as ordinal, or graded response, by the way, counts, censored outcomes, where something has been cut off artificially, zero inflated, where there's more zeros for a pile of counts than there otherwise would be, and then also things that are continuous but skewed. So things like response time, for instance. They have non-integer values, but it may have some sort of tail that makes it not look normal. So all of these things have a model to go with it. So if we go back to what we started with at the very beginning of the semester, what you have to assume in order for the general linear model to give you accurate results, 3 things about the E's, right? Independent, normal, constant variance. So far this semester, we've fixed independent, right? We add more piles of variance, and so then they're independent. And we fixed constant variance because that's what random slopes do. They imply non-constant variance as a function of a predictor. Now we're fixing the normal part. So if you need a new model, you're in luck. So here are the 3 parts of generalized multi-level models and terminology to go with it. First up, some kind of other distribution for the conditional distribution besides normal. So the reason this is relevant is for outcomes that are bounded. We have to make sure that we pick a distribution that matches the possible values of the outcome. In order to get the correct standard errors for the fixed effects, they should match. You can still think about this as the model for the variance, even though you may not always have residual variance at level 1 as an estimated quantity. So for instance, for binary outcomes, level 1 variance is determined by the mean. For count outcomes that follow a Poisson conditional distribution, their level 1 variance is also determined by the mean. In others, it's estimated. So the point is that we're trying to pick another distribution for level 1 that better matches the range of the values that the outcomes can be. That's the big picture. Next is links, the link function. It's written in notation as G with a dot in it. It is a transformation. However, it is not a data transformation. It is a model transformation. What it does is take an outcome that is bounded and stretch it in a way that it becomes unbounded and predictable by a linear model. So it's transforming the predicted y. It's transforming y hat, so to speak. It's not transforming y itself or x itself. For example, for binary outcomes, each case can only have a 0 or a 1. The model is going to try and predict the probability of getting a 1, but the model has to understand that that probability is bounded 0 or 1. So there are link functions that change that probability into a continuous scale that's unbounded, such as logit or probit are the 2 that are most common. That probit or logit transform scale is what the model predicts. Then you backwards translate into probability and it stays within bounds. So it's taking something that has boundaries and mapping it onto a new variable that doesn't have boundaries. Now, you have seen examples of this before. Do you remember the Fisher R to Z transformation? Go back in your heads to like intro stat. Remember that? You've heard of it, I know. If you want to make confidence intervals around a correlation, you convert each R to Z, and then you like back convert that thing. Z takes R and stretches it out into positive and negative infinity. That's what it does. It's a link function. Because R is bounded between -1 and 1. So you have seen this before. It creeps into statistics sometimes. But each type of outcome is going to have a different kind of link function that naturally maps onto it. Same thing with counts. So like the number of times I've said shit today, for instance, that's a count variable. What is the fewest number of times I could say shit in one day? 0, right? Yeah. Can I have a negative shit day? No. I don't know how that would work. So if I'm predicting a count outcome, I have to have a model that understands that the predicted count cannot go past 0. It can't go below 0. So the link function that's used for counts is the natural log. The natural log reels in counts that are extreme, and it takes the counts near 0 and stretches them out that way into negative infinity. But when you back translate into the count, it stays above 0 as it's supposed to. By the way, you've already learned one link function and using it for normal data. It's called identity. If you take y hat and just predict it directly, then it is an identity link function, meaning times 1. A little bit of trivia for you. But that is to say that everything you've learned about general linear models where you don't have link functions can be viewed as a special case of this using an identity link. Meaning, don't change it. Just leave it alone. Multiply it by 1. So link is the transformation. We have a different kind of residual distribution for level 1. And then number 3 is the one you already know. It's the combination of fixed and random effects. It's known as a linear predictor. This works exactly the way that you're used to thinking about it. A 1 unit change in y per unit change in x. The only catch is what y means. It's going to be logit y or log y or some other linked transformed version of y. But once you're in that transformed metric, the linear predictor, the fixed effects and the random effects work just like you're used to. One other thing that changes as a function of this for estimation, REML is dead to you. It's gone. There is no REML for these models. And what it also means is that the fixed effects are part of the algorithm that has to be solved for iteratively. So models with lots of fixed or random effects take longer now, not just random effects. So we are going to be using regular flavor ML. And wouldn't you say, hey, isn't that bad for small samples? The answer is yes. Too bad. We'll talk about estimation later. There are other workarounds that are different than ML that are sort of like cheap and easy versions, but they don't work as well, as you might imagine. Okay, how are we doing so far? Okay, so here's an example. So we're going to talk about single level data first, okay? Because we don't need the complications of multi-level yet. I want to get you used to the idea of links and residual distributions and that kind of stuff first. So let's say that we have a binary variable. We're trying to predict the 1. So the expected mean of the variable is the proportion of people that have a 1. So the probability of a 1 is what we're predicting. So for instance, if I had a model for the probability that I'm getting a 1 that looks like this, beta 0 would be the probability of a 1 when x and z are 0. Beta 1 would be the change in that probability per unit change in x. Beta 2, change in the probability per unit change in z. Cool, right? Sure. What could possibly go wrong? Well, First off, linear. A linear relationship between x and the probability of 1 is logically impossible. Because if we have a 1 unit change in y per unit change in x, eventually you're going to get to the point where the line goes out of bounds. Can you have a probability of 1.2? Can you have a probability of negative anything? No. So the line only works for so long. It has to shut off though. It has to respect the boundaries. So what we really need is a line that looks like the one on the right, where it slows down as it approaches the asymptote from either direction. This shape, this S-shape curve, is known as a logistic curve. And that is exactly what this model is going to give us. How it happens is through two transformations. So probability is bounded on both ends. Can't go below 0, can't go above 1. So we need model predicted outcomes that obey those boundaries. Okay, cool. I'll solve this problem. First, we take probability and transform it into an odds ratio. So an odds ratio is the probability of a 1 over the probability of a 0. You saw these back in chi-square categorical data. They're effect sizes for contingency tables. Cool. So for instance, if the probability of a 1 is 0.7, then the odds of getting a 1 are 2.33. The odds of getting a 0 are 0.429. So what this transformation does is extend the right side, because odds are bounded at positive infinity, but the left side is still bounded at 0. So it's like halfway there. Not good enough. Some genius figured out that if you take the natural log of the odds ratio, that thing goes from negative infinity to positive infinity, and it's symmetric about 0. And that is your new best friend, the logit. Say it with me. The logit. It's your new best friend. Now, I had a grad student once vehemently argue with me that because what you do is take the log of this thing, it is the log it. I will accept log it also. There you go, Ryan, in case you're listening. But no, this is the logit. It is the log of the odds of the probability of a 1. The log of the odds of the probability of a 1. That's what it is. So it is symmetric about 0. So here's a picture that maps logits onto probability. So a probability of 50-50 corresponds to a logit of 0. The logit is symmetric around 0. It speeds up as it gets to 1 and speeds up as it gets to 0 to the same extent. So here's just some of the predicted values from this table. A logit of 2.2 corresponds to a probability of 0.9, whereas a logit of negative 2.2 corresponds to a probability of 0.1. So 90% versus 10%, 2.2 versus minus 2.2. That's what I mean when I say it's symmetric. Likewise, probability of 0.99 corresponds to a logit of 4.6. Can you guess what a probability of 0.01 would be? Negative 4.6, yeah. So this logit metric is not really intuitive in the sense that the numbers have immediate meaning, but what it does is take probability and stretch it forever. Like this. I stole this from your textbook a long time ago. It's still one of my favorite pictures. The top is probability scale, and the bottom is logit scale. And it shows how the mapping is nonlinear. In other words, the transformation of probability to logit is nonlinear. So a bigger change in probability corresponds to a smaller change in logit. And as you continue a 1 unit change in logit, it corresponds to a smaller and smaller change in probability as it approaches the asymptote. So logits can go on forever. So probability of 0.5, 50-50, corresponds to an odds of 1, which corresponds to a logit of 0. So these are 3 different scales on which to describe the distribution of this outcome. It's almost like Celsius, Fahrenheit, and can I say Kelvin? Does that work for this analogy? Or centimeters, inches, and Lisa feet or something, some other metric. You have to know the conversion to get back and forth, but there's a nonlinear transformation. So what we do is build a linear model that predicts the logit. So I can have a predicted logit of 3. But when I back translate that logit of 3 to probability, it's still 0.95. I can have a logit of 4, and it back translates into about 0.97-ish, I think, given us this thing. By the way, back translate is my way of saying inverse link. That's the technical term. I also am fond of saying unlogit it. So if you go from probabilities to logit, that's one way. If you want to unlogit it, you go back to probability. But it's inverse link. So we've solved one of the problems. Your new best friend logit makes it so we can predict the logit of y linearly, but when we back translate to probability, it looks like this S-shaped curve. And literally that is how I made these pictures. Logit y is the y-axis of the left picture, which translates into probability of y on the right. Okay, so that's one problem solved. Now the other one. Residual is supposed to be normal with constant variance. So if I'm using a general linear model to predict a binary outcome, that ain't gonna work. Because for any value of y, there can only be, any predicted value of y, there can only be 1 or 2 e's, right? It's either above or below, because there's only 2 values of y. So e's can't be normal, and they have to be dependent on the mean. The variance of a binary variable is maximal at 50-50. The variance is 0.25, because the variance of a binary variable is the probability of a 1 times the probability of a 0. That's how you find it. The variance shrinks the closer you get to 1 or 0. So this is to say, if you have a normal distribution, right, what are the 2 parameters that are supposed to describe a normal distribution? Mean and standard deviation or variance, right? And they're separate, right? You need both. Variance is a function of the mean. There's only one thing you need to know. If I know the probability of people who got a 1, I know the variance. So not only does variance not have to be estimated, it can't be the same number across all the data. It has to stretch and shrink along with the predicted outcome. So we need a distribution besides normal that allows the mean and the variance to depend on each other in that way. And this is going to be our new friend, Bernoulli. It's a dude. He named a distribution after himself, or someone else did. That's why it's always capitalized. So I stole from Wikipedia each of these pictures. Here's a normal distribution, characterized by mean and variance as separate parameters. There's the formula for normal. I find it intriguing that normal is the thing that gets taught first, but it has one of the scarier formulas, relatively speaking, like for intro stat. Whereas Bernoulli, there's a picture on the bottom of Bernoulli. It only has one parameter, p, the proportion of ones. So for instance, the blue line here, if I have 75% of the people who got a 0, what percent got a 1? 0.25. If 50% got a 0, how many got a 1? I only need to know one of them. And the PDF that gives me the probability is the probability of a 1 if that's what you got, times the probability of a 0 if that's what you got. And that's it. So if we swap out a normal distribution at level 1 for our conditional distribution with this Bernoulli instead, that solves the problem, because then the e's aren't supposed to be normal. They're not going to be. They're going to follow this distribution. And this distribution has non-constant variance as well. The one consequence is that residual variance is gone. Now think about how that's going to affect us down the road. What kinds of things do we use level 1 residual variance for? I can think of at least 2 right off the top of my head. Things I make you calculate and stick into homework assignments that have to do with level 1 residual variance. ICC is one, yeah. The bottom of the ICC formula has a residual variance at level 1 in it. How about effect size? Proportion reduction in level 1 residual variance for level 1 fixed effects. Oh shit, what are we going to do? It can't go down. Add 1 to the shitometer. You know what happens instead? Everything else has to go up. So there are various ways people have developed in this distribution, or more specifically in logistic regression, which is what it's called when you pair a logit link with the Bernoulli conditional distribution. They have developed various kinds of R-squares. They're all sort of squirrely because variance can't go down. There's not one unique answer for them. So you'll get different answers across methods of R-squared because variance is not estimated. So this model that we're talking about then, if I start with a linear model, that, and I change it to add a logit link and to swap out normal for Bernoulli, it is going to look like one of these 3 things. There's actually 5 things on this slide, and you know why I put all 5 here? Because I was so pissed when I figured out these are all the same. Because they look really different. And I'd see one in one textbook, and I'd see another one in another program, and I'd be like, here's what happens. If we start with just the regular linear predictor that we had before, so fixed intercept, fixed slopes, all copacetic, that thing predicts your friend the logit. The log of the odds of the probability of a 1. So beta 0 is the expected logit when x and z are 0. Beta 1 is the change in the logit for 1 unit change in x. Beta 2 is the change in the logit for a 1 unit change in z. And then you get someone that says, but what the hell's a logit? And you say, well, let me unlog that for you. And we get into odds. So if you take your slopes and unlog them, or what most people would say exponentiate, I think, exp to the, you get this version of the model in which what you're predicting is odds, not logits. And the coefficients are multiplied this way. This drives me crazy. I can't handle coefficients that are multiplied. Odds are very non-intuitive to me. So to me, it's like, I don't know what that is either. I'm just going to skip all the way down to probability. Because if I put up a graph with probability as the y-axis, even my mom knows what that means, right? That's an intuitive metric. What is the probability that my mom will understand this graph? 50-50, but better than logits or odds. And so the y side is nice and intuitive. But then you get to the x side and it's a big old mess. E to the model over 1 plus e to the model. And then, if you want to write it more simply, if you stick a -1 in the e to the model part on the bottom, somehow the top cancels out. And so that's yet another way this is written. Now, for those of you who've taken IRT, does this look familiar? IRT gives it to you this way. Logistic regression gives it to you one of these other ways. but it's all the same. It just depends on what is the outcome you're predicting. So what I end up doing is a combination of all three. I interpret the coefficients as predicting logits because then you can use the familiar 1 unit change language and everything is cool. Odds ratios are commonly used as measures of effect size, particularly in medicine. And if I want to show pictures of what my model says, I back translate predicted logits to probabilities and I make pictures with probability. That just means that my slopes are going to be nonlinear, which makes it interesting to look for interaction terms because then it's less obvious what they are. Okay. So, what's a logit? Log of the odds of the probability of a 1. I say 1, but this is one of the things you have to check. Some software packages default to predicting the probability of a 0. I know, right? That's crazy. So one of the very first things that I will teach you to do is to produce an empty model. Just so you can see if it's doing the 1 or the 0, because it will match your data. If you use a single level empty model, you can figure out which way it's going. All right, one more time. Logit is the log of the odds of the probability of a 1, damn it. Okay. Good for now. We'll pick this up on Thursday. So office hours start now. Let me know if you need anything. That is random.